All right, so the next thing we need to take a look at, which may seem sort of counterintuitive, or you may be asking yourself, why are we even looking at this now? In order to understand electrons, we first of all need to take a step back and take a look at the nature of light. And we're going to take a look at some of the properties of light. And as we'll see down the road, some of these properties are the same properties or characteristics that things like electrons possess. And as of right now, that's not necessarily something that we would necessarily predict. But it is important to grasp some of these concepts now. We can apply them to electrons a little bit later on. So when we talk about light, we normally refer to the light that we're able to see. That's visible light. So the visible light that we observe with our eyes is actually only just a very, very, very small part of what's known as the electromagnetic spectrum. And we often abbreviate electromagnetic as the EM spectrum. And that spectrum is a continuum of energy, wavelength, frequency, etc. So if we take a look at one such picture of the electromagnetic spectrum, this is from your textbook, we will see that the visible light is actually an extremely small part of the spectrum as a whole. Okay, so for example, visible light, the light from the rainbow, Roy, G, Biv, whatever uh, your little mnemonic that you use to help remember the different colors, it only makes up this small percentage here. The vast majority of the electromagnetic spectrum, from gamma rays all the way over to the visible light, and then from infrared radiation all the way over to radio waves, those are things that we cannot observe with our eyes, for example. So for all intents and purposes, they seem invisible to us, but they are around us all the time. So visible light, for instance, going from red all the way to orange. So red is over on this side of our little thing here, a color spectrum: red, orange, yellow, green, blue, indigo, violet, right? So if you think about your the Roy G. Biv, which I think some of us know. If you don't know, that's fine. So red, orange, yellow, we have green, blue, indigo, and violet, right? So we've blown it up down here, but it really only makes up a very small percentage of the EM radiation spectrum that we have. And the light that we see is composed of several different wavelengths of light. So violet light, for example, or closer to the blue end of the spectrum, has a wavelength of about 400 nanometers. On the red end of the spectrum, the wavelength of that light is about 700 nanometers. So outside of those two sort of bookends of visible light, we have other types of electromagnetic radiation. So we have things like ultraviolet light. Okay, so UV, right? That's light, sunlight, for example, and that's the type of light that causes damage to your skin, causes skin cancer, etc. X-rays, right? Also very damaging. That's why you can go to the dentist or you get an X-ray at the doctor's or something. They minimize your exposure to it, so you're not unnecessarily exposed to too much of that type of electromagnetic radiation. And if you look at the wavelength of ultraviolet light and X-rays, they are extremely small, right? So this is in nanometers now. So tens of nanometers for UV light, tenths, 1/10 of nanometers for X-rays, and then way even smaller for things like gamma rays, which we talked about in the nuclear radiation section. On the other end of the spectrum, we have longer wavelengths, so things like infrared, which we often abbreviate as IR. We usually associate that with like heat signatures of things, right? So you have a heat camera or something, you're looking at infrared radiation. So on the order now of thousands of nanometers. Microwaves you have in your, microwave ovens at home, for instance, and then radio waves on the other end, right? These are in the air all the time. These have very, very, very large wavelengths on the order of billions or thousands of billions of of nanometers long. And we'll talk about what wavelengths are in a second. So this is the continuum of EM radiation. Visible light only makes up a very small percentage, a very small fraction of electromagnetic radiation. So when it comes to light, light travels at a particular speed, which we abbreviate as c. So lowercase c is the speed of light through a vacuum, and that's a constant, meaning it doesn't change. And that's normally rounded to 3 sig fig, so 3.00 times 10 to the 8 meters per second. Okay, so that's a very, very fast speed. Some people think of it as sort of the speed limit of the universe. Okay, you do not use this if you get pulled over by the cops for speeding. Don't say that, oh, it wasn't even close to the speed limit of the universe. There are speed limits on roads that you need to adhere to. But this is the speed of light. Okay, it's through a vacuum. So 3 times 10 to the 8. So in other words, 300 million meters per second is how fast light travels. So we talked about wavelength a little bit in the chart above. The other thing that you may have seen on the chart is something called frequency. So wavelength, frequency, as well as the speed of light c are all related by an equation, and that's this equation here. So the speed of light c is the product of the wavelength. So c, the speed of light, is equal to this thing. This is called lambda, which represents that's a Greek symbol. That means the wavelength, which we alluded to before, times. So this v here kind of looks like velocity that we saw previously. This is not v. This is another Greek symbol called nu, nu, and that represents the frequency. Okay, we'll talk about what frequency is here in a second. So you multiply the wavelength by the frequency, we end up with the speed of light. So if we look at units, okay, wavelength is often expressed in meters, and then frequency has units of seconds to the -1, which is the same as 1 over second. So if I multiply meter times 1 divided by a second, guess what I end up with? Meters per second, right? And that's the unit of speed, which we saw up here, meters per second. The unit second to the -1 or 1 over second, this is also known as the hertz, okay, again, named after a person, and that's abbreviated HZ for hertz, not the rental car company, but in this case, it's a unit of frequency. So all forms of electromagnetic radiation will adhere to that speed limit to all travel at the speed of light, 3 times 10 to the 8 meters per second. What they're going to vary or change by is their wavelength and their frequency as well, because whenever we multiply the wavelength by the frequency, we should get this constant, right? C here is our constant speed of light. So let's take a look at each of the characteristics now of waves. So we're going to take a look at both of those, wavelength as well as frequency. So if you think of a wave, right, you can imagine sort of like a wave in an ocean. So imagine an ocean wave, and that's a good analogy to what we're going to try to discuss here. And it's coming along. So for example, diagram A kind of shows you the wave. So it goes up, goes down, goes up, goes out, kind of bobbing throughout the ocean. So when we look at a wave such as A, we can find any place along that wave. So think about, a wave, the top of the wave here being the crest or the peak. Okay, so that's going to be the top of the wave. And then the bottom part of it here is called the trough. So if we think of any point along the wave, and it's easiest to think of either a peak or a trough. So let's think about, we'll highlight this in, say, green. So this point right there. So that's the peak or the top of it. If I look along this wave and I find another peak that's closest to it, so like, for example, here, the distance between two adjacent peaks, which is the same distance between two adjacent troughs, right? So the distance between two equivalent points along the wave, that is known as the wavelength. Okay, so you don't have to choose the peak or the trough. You can pick any point along the way. So for example, if I pick this point here, okay, an equivalent point further down would be this point there. And that is the length of the wave as well. That is also going to be the wave. They all represent the same distance. That's the wavelength of that wave. Another characteristic we'll see for waves is something known as the amplitude. Okay, and the amplitude is simply the distance from sort of the midline. So this black line there, that's your midline or your reference point. Okay, to either the top of the peak or the bottom of the trough. Okay, this is the amplitude. Either of these could be the amplitude. And you can think of the amplitude for in the case of light as how bright the light is. Okay. Bigger amplitude, brighter the light. So brightness of the light. So we have wavelength, we have amplitude. The other thing that we're going to see with our waves is called a frequency. Okay, so frequency is how many of the wavelengths pass by a particular reference point per second. Okay, so our frequency how many wavelengths pass by per second. Okay, so if we imagine, I'm going to erase a bunch of stuff here. So imagine that the time between the beginning of our midline and the end of our midline corresponds to 1 second. Okay, so in our little diagram here, from this point all the way over to that point, this is 1 second. Okay, for wave A, how many wavelengths actually pass by or in that 1 second? Well, if we start here, we find an equivalent point. That's an equivalent point. That's 1, and then 2, and then 3, and then 4. Okay, so for wave A, the frequency there is 4 wavelengths per second. So we would say 4 second to the minus 1, which is the same. Second to the minus 1 is the unit of hertz. So this would be 4 hertz. That would be the frequency of wave A. If I look at wave B, right, again, this time here is 1 second, same as above. So if I count the number of wavelengths passing by that 1 second, I have 1, 2, 3, 4, 5, 6, 7, 8. So for wave B, it's 8 per second or 8 hertz. And then for wave C, again, same distance or same time. And if I count the number of wavelengths, we'll use a different color this time. We'll see there's my first, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So for wave C, there's 16 wavelengths that pass by per second, so the frequency there is 16 hertz. Okay, so we can count these obviously in these fairly simple cases. A couple things to note about the relationship between the wavelengths and the frequency. And this is going to be really, really important when we start looking at relationships between things, okay? So we have our three waves, three different forms of radiation, A, B, and C. Now, what do we notice when it comes to wavelength versus frequency? Well, in the case of wave A, it has a much longer wavelength than both wave B and wave C. However, the frequency of wave A is less than that of wave B and wave C. So what we can say is, so if we compare and contrast wavelength and frequency, what we can say is as the wavelength, okay, so as we go from A to B to C, what's happening to the wavelength? Well, it's decreasing, it's going down. So as the wavelength goes down, what happens to the frequency? Well, the frequency goes up. And the reason why is because when I multiply these two things, I have to end up with the same number, which is C, right? So remember that equation, C equals the product of the wavelength times the frequency. So if this thing, if the wavelength goes up, I'm sorry, goes down, okay, the frequency has to accommodate for that by increasing. And then similarly, if we can predict then if the wavelength goes up, well, then the frequency has to go down, right? So this is called an inverse relationship between frequency and, well, the wavelength and the frequency. Okay, and you probably, if you were looking closely at our picture above of the electromagnetic spectrum, you probably would have noticed that. Okay, so if, for example, I look at gamma rays that have a wavelength of 10 to the negative 3 nanometers, right? So this is a very, very, very small, so this here, okay, is a small wavelength, so small lambda. What about our frequency? Frequency is 10 to the 20. That's a large nu. It's a large frequency. If we go on the other end of the spectrum, right, what we see for radio waves, for example, is the opposite. So my wavelength here is large, okay, but my frequency compared to the other side of the spectrum, the frequency is small. Okay, so as we go, and we can look at both ends of the spectrum now, as we go from small wavelengths, small wavelength to large wavelength, the frequency goes from large to small, right? So kind of like a seesaw, right? One goes up, the other one goes down. That's an inverse relationship, and that's critical to know about wavelength and frequency for electromagnetic radiation. So both, well, I'm sorry, our electromagnetic waves and all of the ones we talked about before on a little diagram here, these are all examples of electromagnetic radiation. Now they're called electromagnetic because they have both an electric field component and a magnetic field component. And these, okay, just like they're oscillating in this wave type form, these components are perpendicular to each other. Okay, so both, we say, are mutually perpendicular. So if we were to imagine, so the thing in pink here would, that frame of reference is along the Z and the x-axis. Okay, so that represents the electric field component. And if you think about your the magnetic field, so that's at right angles, right? So that's what perpendicular means, at right angles. That's 90 degrees right there. And that then is going to be the magnetic field component, again, oscillating in a wave type form, perpendicular to the electric field component. And that combination of electric field and the magnetic field is going to be important when we start looking at properties of the waves a little bit later on. We start looking at electrons also. Okay, so one more thing, one more experiment. We talked about lots of experiments early on. One experiment that actually helped to show the wave nature of light. So in other words, this experiment showed us that light actually does come in the form of waves, is something known as the double slit experiment. And it's a very simple experiment. I will come back to the double slit experiment later on in this section. But it's actually really simple. So we have here down at the bottom, we have our light source coming this way. And what they did was they shined that light source through against a wall, if you will, or a barrier. And in that barrier was a little opening. It was a small opening right about here. And obviously the light is going to be blocked by the most of the wall, but it's going to go through that small opening. And then behind that wall, there's another wall. So this is wall one, and this is our second wall. And in that second wall, there are actually two openings. So in other words, a double slit on that second wall. Now, when they perform this experiment, shining the light from one side, allowing it to go through that first slit, and then allowing it to go through the two slits in the wall behind, what they actually observed was something that looked like this. And what this showed was, instead of what you could imagine, if you just shine the light from this end, it should really go all the way through, and then it should be blocked right here. Right? That's what one would predict. So if you had an observer over here, this is your eye, okay, you really shouldn't see anything. This whole thing should be black because the light is blocked right over here by this second wall, right, that I'm highlighting in yellow. But that's not what they observed. They actually observed alternating patterns of bright light and dark spaces. Okay, so we have a bright light over here, and then a dark space, bright light, dark space, bright light, dark space, etc., all the way through. Now, they had to come up with an explanation for this, and the explanation stems from a characteristic known as diffraction. And diffraction is what happens when a wave, for example, goes through a small opening. What happens is that wave actually sort of bends through that opening, right? So if it's a wave coming in here as our normal waves, it actually adopts this sort of concentric form after that first aperture or that first opening. When it hits the second, now we have some waves over on this side, they start to diffract as well. And then over here in the second slit, they diffract as well. And what happens is when these two diffracted waves now, they can interact with each other. Okay, so we have our diffracted waves on this side. And they can interact. And the term that we give to that is interfere with each other. Now, to understand that interference, we need to think about how waves actually work as well. Okay, and you probably know this from experience, but let's take a look at it. If I have a wave that kind of looks like this, okay, and then I have, let's finish the wave here, and then I have another wave, okay, that is identical to it, but it also coincides with that wave on top. Okay, so all the troughs, okay, so all the troughs line up. I'm sorry, all the peaks line up, all the troughs line up, all the peaks line up, all the troughs line up, all the peaks line up, all the troughs line up, etc., all the way through. Okay, these two waves, waves A and B, we say that waves A and B are in phase with each other. So they actually add together And the term that we get when that we say that they're in phase or they add together is we say that there is constructive interference. So what happens then if we add the peaks together and the troughs together? Well, then guess what happens to the size or the amplitude of the resulting wave, right? The amplitude increases now. It's now one bigger wave, right? So we have now the amplitude is much larger than it was in either of the first two cases. Okay, and that happens when waves are in phase, when the peaks overlap and when the troughs overlap as well. We have constructive interference and we have bigger amplitude. So in other words, the light then should appear very bright. Now, the other way that waves can interfere with each other, if you have two waves right next to each other, is if instead of the waves being in phase with each other, where they overlap, maybe now a peak overlaps with a trough. So there's a peak, and then here's a trough. There's a trough, there's a peak. There's a peak, there's a trough. There's a trough, there's a peak. There's a peak, there's a trough, and you get the idea all the way through. Okay, so here we have now peaks overlapping with troughs. And as a result, they cancel each other out. Okay, so what happens then? We say that those waves are out of phase. And they cancel each other. And what do you think that wave, that resulting thing would look like? Well, it actually looks just like a straight line. There isn't any peak or trough. So we refer to that because by all intents and purposes, what we've done is we have destroyed both of those waves because the peak cancels out the trough and the trough cancels out the peak. So we have what's known as destructive interference. And you can probably guess what destructive interference would look like. It would appear dark. So we have both of these happening when that initial light source producing that wave diffracts through that first opening, and then it diffracts through that double slit. These two resulting diffracted waves then interfere with each other in a constructive way, where we see the bright spots. They also interact with each other in a destructive way, where we see the dark spots, okay? And that sort of goes throughout the entire little wall here. If we're observing the wall, we would see that pattern. And that pattern is known as a diffraction pattern. And that happens with waves. Because they were able to observe this, they were able to conclude, yes, light possesses wave-like characteristics. Okay, so it's a very simple experiment, but in order to explain what's going on, we had to use what we know about waves and destructive, constructive interference to explain that. All right, so the thing that we need to know about, other than qualitatively what's going on, quantitatively, how we're able to use our wave equation, C equals lambda times V, we should be able to use that equation, rearrange it to solve for any unknown. Okay, so make sure you can rearrange the equation C equals lambda times nu. Okay, so for example, given the information about this particular laser, the wavelength of the laser beam here is 532 nanometers. we need to find the frequency, okay? So we're given in this question wavelength. We need to find the frequency, okay? So we need to use a relationship between wavelength and the only relationship that we've talked about here is C equals lambda times nu. If we need to find nu, okay, we can rearrange that equation. We divide both sides by lambda. So nu then is equal to C over lambda. Keep in mind that your C, your speed of light, is in meters per second. Okay, so if you're given your wavelength, you want to make sure that you convert that to meters. All right, so if we're given our wavelength here in 532 nanometers, we do the conversion to meters. Okay, so we divide by 10 to the 9, or we multiply by 10 to the negative 9. I mean, you should get a very small value for meters, okay, so for the negative exponent. And then we take the speed of light and we divide it by that wavelength in meters, and we end up with a frequency of 5.64 times 10 to the 14. Now, does this number make sense? Okay, frequency should always be a fairly large value. If we go back to our table oops, sorry, I went right by it. All right, our frequencies here start with radio waves at 10 to the 4, they go all the way up to 10 to the 20. So frequencies are normally fairly large numbers. Wavelengths are always going to be on the other end of the spectrum, usually very small. You have some large wavelengths, but they are, going to be where we encounter microwaves, radio waves, etc. This is you're asking about the wavelength of a laser, which is going to be over on this side of the spectrum. Okay, so the answer in this case does make 5 times 10 to the 14. That makes sense both in terms of the units. So our unit that we end up with here is going to be second to the -1 or hertz. Number makes sense in terms of the magnitude as well.